Alright, let's rock and roll with another one of these sample problems for Chapter 12. This is going to be number 75 in your textbook if you want to follow along. It reads something along the lines of this. There is a solution that's prepared from 4.08 grams of chloroform, this is the formula, the molecular mass, and 9.29 grams of acetone. You mix those two things together to make the solution, or the mixture. Here's the formula for acetone. Its molecular weight is a little over 58 grams per mole. We're then told at 35 degrees Celsius, pure chloroform exerts a vapor pressure, P0, 295 torr, and at this temperature, pure acetone's vapor pressure is 332 torr. We're supposed to assume what's called ideal behavior and calculate expected vapor pressures for each component above the mixture, and also the total vapor pressure that's exerted by both components, okay? So you'll see this terminology of ideal behavior a lot in this chapter. And again, I mentioned this in class, but what that basically means is the enthalpy of solution, or the heat of solution when these guys are mixed, is very close to zero, okay? Which basically means the intermolecular forces that exist in the mixture are very similar in strength or magnitude compared to before we mixed the case, where we had the pure solute and solvent, okay? So that's what we mean in this case by this ideal behavior. And basically the significance of that is that this summing of the partial pressures as computed through Raoult's law, that business will work, and we'll get a very good estimate of the experimentally measured vapor pressure as long as the solution follows this ideal behavior. But if it doesn't, the experimentally measured vapor pressure is going to deviate from what we would predict through the type of calculation that we're about to do, okay? We'll get into that in a little bit here, but I want to just mention that at the start. Now, it might be helpful to have a mental picture of what's going on in this experiment. So I do this little beaker here. There's a beaker, there's a mixture of the acetone and chloroform. Both of these are going to be liquids, so there's going to be a liquid at the bottom of this beaker. It doesn't even need to be necessarily filled up this much, just as long as we have enough of this mixture to basically establish an equilibrium between the liquid and the vapor phase, okay? So to achieve that, what I've done is I've put a piece of glass on the top of this beaker that completely seals it off, okay? And we basically wait long enough such that the evaporation and the condensation process that's occurring inside this beaker reaches an equilibrium, and we establish a consistent pressure inside this headspace, or this vapor phase, okay? So some of our molecules will evaporate, become a gas. They will exert a pressure, and when that vapor is in equilibrium with the liquid, that's referred to as the vapor pressure. And of course, it'll be a mixture because we're going to have both acetone and chloroform down here, and also up in the vapor phase, it's also a mixture. The composition of the two phases need not be the same. In fact, most of the time they'll be different. And this type of problem allows us to actually compute what the composition in the vapor phase is from a known composition of the liquid phase. And that's what this problem really is all about. Now, as I read the problem, I know many of you have some confusion of whether or not one component's important or multiple components are important to determine the total pressure. And I look through this problem and I instantly see that I'm giving two values for the vapor pressure of the pure liquids, and that tips me off right away that I've got a two-component mixture, each of which are volatile. Each can exert a vapor pressure of their own, so I'm going to have to work the calculation twice, one for each substance. If I was only given one P0, that's a pretty good indicator that I'm only going to have to work it once for that volatile component. The other component is going to be then considered non-volatile, and it doesn't exert vapor pressure that's measurable or important in that case, okay? So just things to look at when you're faced with a problem, okay? Just little hints. Okay, so now how do we tackle this business? How do we tackle this? Well, we're again going to invoke this business of Raoult's law. The Raoult's law relationship allows us to compute the vapor pressure over a mixture for volatile components, and it's based upon the mole fraction of the component of interest. So mathematically, what the Raoult's law relationship tells us is that the vapor pressure of the chloroform in this vapor phase above this mixture, okay, can be found or estimated by multiplying chi, the mole fraction of the chloroform, times the P0 for the chloroform. P0 is the vapor pressure of the pure solvent. I can use that equation for chloroform. I can also use that equation for acetone. Same equation, just different numbers because my mole fraction for acetone will be different, as will my P0 term. I'll be consistent with it up here. Because acetone and chloroform do not have the same vapor pressure for the pure solvents. So I'm going to use this equation twice, once for acetone and once for chloroform, solve for these numbers, which again refer to the partial pressure in the vapor phase of both this liquid. Okay, so that's what I'm solving for. So don't lose sight of that, okay? Now, if I'm going to do that, it becomes clear right away. I need to know my mole fractions for both components, okay? And when you're working these types of Raoult's law type problems, solving for mole fraction is almost always going to be one of the first things that you need to do, okay? So to achieve that, I need to figure out how many moles of each component I've actually got. So let's do the calculation for chloroform first. Number of moles of chloroform is equal to the grams of chloroform, which is 4.08 grams, divided by the molar mass in gram per mole units. The molar mass of my chloroform, it's a pretty heavy molecule. It's got all that chlorine, so it's 119.38 grams per mole. If I do the math on that, the number of moles of chloroform is 0.03417 mole. Okay. Likewise, I can compute my moles of acetone. I'll do that down here, so we're not confused. Number of moles of acetone is my mass of the acetone that was present. Looks like I had 9.29 grams of the acetone. Of course, I need to divide that by the molar mass of the acetone to convert it to moles. Molar mass is 58.08 grams per mole. When I do that computation, I find that I got 0.1599 mole of acetone. Again, I'm not paying attention to sig figs here, just taking the numbers off my calculator, okay? So I have this many moles chloroform, and that many moles of acetone. Now I can compute my mole fraction readily, because if I know my equation for mole fraction, it says that chi for a component, say CHCl3, is equal to the mole of that component divided by the total moles of all component present in my mixture, okay? So if I'm going to do this for the chloroform, my moles of chloroform was 0.03417. I'm going to divide that by the sum of the moles of chloroform plus the moles of my other component, which in this case was the acetone. That was 0.1599. If I go about solving for mole fraction then, for the chloroform, I find that my mole fraction is 0.1761. And that's for my chloroform. So coming back over here, that number goes right here for my chi, because that's my mole fraction, 1761. About 17.6% of all components was the chloroform on a mole basis. I also know this number, so I'm going to plug that in right away. This was given to me in the problem. It's the vapor pressure of the pure solvent. And if I look back through the problem, I believe I am told that. Okay, so pure chloroform has a vapor pressure 0 of 295 That number just goes right there. Okay. So that's wonderful, because what I can do now is I can complete that computation and find 51.93 torr is my expected vapor pressure of my chloroform. Okay, this is a different calculation below the line, so don't let that interfere. Now, we need to do the same thing for acetone, all right? We know in the problem that the P0 for acetone, that's the vapor pressure for the pure substance, was 332 torr. So I can write that in. But I still need to know my mole fraction for the acetone. So I'm going to need to solve for that, okay? It's not a freebie, I've got to solve for it. So if I want to solve for the mole fraction of acetone, I can. I guess I can do that work right here. Okay? It's just the moles of acetone divided by the total moles of everything. So previously, when I took the mass of the acetone, I figured out, and I divided by the molar mass, I figured out I had almost 0.16 moles, or 0.1599 moles of acetone. And of course, the total number of moles of all components that are present is that number plus however many moles of the second component I've got, in this case chloroform, and I found that I had that many moles of chloroform. So I have to add that to my moles of acetone. I'm going to do that down in the denominator because that's the definition for mole fraction. Okay. So I do the division and multiply that by my P0, which is my 332. My mole, so that's going to equal, well, my mole fraction, first off, will equal, for the acetone, will equal 0.8239. And 332 torr is still my P0 term, still my vapor pressure of the pure solvent. And if I finalize this by doing that calculation, getting that product, it's 273.55 torr. And again, that's just a number that comes off my calculator, okay? And that's my P acetone. Okay, so in this vapor, above the liquid, there should exist a partial pressure of acetone of about 273.5 torr, plus a little less than 52 torr exerted by the second component, the chloroform. Okay? So now we know something about the pressure of the gas that's inside that headspace. I'm going to erase this to keep moving on. The question also asks, what is the total pressure of both components? That's pretty easy. All we have to do to solve for that is add them together. So 51.93 is from our chloroform, 273.55 is from our second component, the acetone. Okay, so if we add them together, total pressure is 325.48. Torr being the unit, which is the pressure unit. Okay? Makes sense. Now, if you ever need to compute the mole fraction in the vapor phase, you actually can. Okay? It's pretty easy too, because the mole fraction of component 1, whatever component that is, it could be acetone, it could be chloroform, okay? But the mole fraction of a certain component in the vapor phase, this is specific to the vapor phase, okay, can be found by the ratio of component 1's partial pressure divided by the total pressure. So if I wanted to find the mole fraction of chloroform in this vapor, I would simply take the partial pressure of chloroform, 51.93, substitute that in there, and divide it by the total, which is 325.48. Okay, so that's a useful equation as well that you might need to come across using from time to time in your homework or on an exam or quiz or something of the sort, okay? But surely we can compute the mole fraction in that vapor phase. The neat thing about this is that the mole fraction in the vapor phase will be different typically than the mole fraction in the liquid phase. The vapor phase tends to be more enriched in the more volatile component, because you can think of that as evaporating better if you want to think of it that way, okay? But it's enriched in the more volatile component, and that is pretty typical for this type of system. Now, some additional things that this problem deals with, okay, that I want to get into here at the tail end. We've done all the quantitative work now. We talked about, what's the total pressure, what's the partial pressure of each particular gas or each substance. We talked about computing the mole fraction in the vapor phase if we need to through using this equation. Okay, so we've made a lot of progress. But your book goes on and asks you some additional questions, basically, okay? If I'm reading on in question 75, that's the one that we're working right now, it says that they actually went into a lab and measured the vapor pressure of this vapor. When they did that, I don't think I'm following along in 75, right? Yeah, the experimentally measured total vapor pressure was 312 torr at 35 degrees. So they went in the lab and they actually measured, and the results said 312 when they measured the vapor pressure of the components in this vapor. Now, in our computation, we estimated about 325 and a half for the sum of the components. That should be the vapor pressure in here, but when we measure it, it's different. It was only 312. So the measured vapor pressure was lower than what we computed, okay? So back to this business of ideal solutions. Remember I said that for an ideal solution, the enthalpy of solution or the heat of solution, that's the heat upon mixing of the components, is close to zero. If the solution's ideal, that's true. And the result that we get should agree very well with the experimental value. But we see in this case there's a little bit of difference between these two. So what that tells us is that this assumption of perfectly ideal behavior was probably not correct. Okay? Now this provides a model for predicting what the vapor pressure might be over the solution. But when we actually measured it, we found that the true value deviated a bit from what we predicted. So these equations, again, are kind of like a model system. Don't lose sight of that. It doesn't always represent perfectly reality, okay? But another thing that's interesting about this is if we know the experimental measurement, and we know what we should have got if the solution was perfectly ideal, by comparing the magnitudes of the two, we can say something about the intermolecular forces that exist in the resulting liquid solution. So in this case, we note that the vapor pressure that we actually observed is lower than what we should have gotten if the solution was ideal. And what that means is that the intermolecular forces that have formed in this liquid between acetone and chloroform are stronger than what originally existed when the acetone and the chloroform were separate. Okay, the new intermolecular forces are a little stronger than what we had originally. And that's why this solution deviates ever so slightly from this true ideal behavior. Okay, so we can actually use the difference between what we predict and what was experimentally measured to say something about the intermolecular forces. So this solution would not be ideal, and the intermolecular forces of the mixture actually are a little bit stronger than what they were to start with when we had just pure acetone and the chloroform interacting with each other, or with themselves, basically, okay? And I know that because my true vapor pressure is lower than what we would have predicted for the ideal solution. Remember, these intermolecular forces kind of like that molecular glue that holds the material together, okay? In this particular case, you can think of that as hindering the evaporation or the volatilization of our molecules, which therefore lowers that vapor pressure down compared to what it should have been, okay? So the intermolecular forces are a little bit stronger there. Okay, so this is just another example problem of a two-component mixture where we're going to use Raoult's law to compute vapor pressures. The key ideas here, understanding both of these components are volatile, that you have to do the calculation for both. To get the total pressure, you have to add together the partial pressures, like we did. This is a key idea here. You may see that in one of the homework problems on an exam, that if you want to know the mole fraction of a component, I just call that component 1. It can be component A, component B. This is one of the substances. If you want to know the mole fraction up in the vapor phase, if you know the partial pressure of that component divided by the total pressure of all components, that's going to give you the mole fraction in the vapor phase. Okay, so that's a useful equation as well. We talked about this ideal behavior versus non-ideal behavior depending upon the intermolecular forces that exist. So that's this problem.